Okay, all righty. I think we could start up now. My name is Alex. I'm the coordinator here at URISA Alberta, programs coordinator at URISA Alberta. And yeah, if you could just maybe in the chat, just let us know where you're connecting from, that would be awesome. I'll go straight up into the introduction of our first speaker. As our first speaker, we're going to be having Nooshin Mashhadi, who is an environmental scientist specializing in environmental remote sensing and GIS and forest structure complexity analysis. She's currently a PhD student at the University of Alberta, and her research is focused on developing novel entropy-based indices for assessing forest biodiversity and complexity using full waveform LiDAR data. Nooshin has extensive experience in interdisciplinary projects, including GEDI, UAVs, and system dynamics modeling, and her work has been published in a good number of scientific journals, and she's been involved in lots of presentations. She's passionate about advancing ecosystem monitoring and continues to contribute to environmental research while fostering collaboration across different disciplines. Nooshin will be talking today on part of our research topic, which is modeling entropy in tropical forests. Yeah, the floor is yours now.
Thank you so much, Alex. Yeah, I'm just sharing my presentation for everyone. Okay. So my name is Nooshin Mashhadi. As Alex said, I'm a PhD candidate in the University of Alberta under supervision of Dr. Arturo Sanchez. My research topic is about modeling entropy in tropical forests. The agenda of this project, of this presentation, would be include of some objective of the project, a little bit introduction about entropy, and then I will introduce Lorenz curve and Gini coefficient. After that, we will talk about my new index, which calls Lorenz-entropy and its application in forest ecological succession. After that, I will talk about how full waveform LiDAR can apply to this study, and then a little bit talk about the result and then conclusion. So the objective of this project was to develop a new method, basically a new index that could talk about structural complexity using a full waveform LiDAR data. And also, plus of that, we was wondering about the ecological successional dynamics of the forest, especially tropical ecosystem. So if I want to talk about entropy, actually the concept of entropy comes from the second law of thermodynamics to the study of the forest ecosystem. Based on this second law of thermodynamics, the entropy of a system always is increasing. And what is entropy? It's called the disorder or heterogeneity in the system. Basically, in the thermodynamics, we believe that whenever we have a closed system, this system the entropy of the system always is increasing, okay? But when it comes to the forest ecosystem, when it comes to the study of the ecosystem, when we are interested to have the lower amount of entropy with high amount of complexity, which creates a sustainable system for us. Based on this definition, and also plus of that, the Lorenz curve and Gini coefficient. What is the Lorenz curve and Gini coefficient? Gini coefficient comes from an economist called Gini, who was wondering about how the income and population are related together and how was the society related to income per each person. And then he created the Gini coefficient based on the Lorenz curve. And as you can see in this image, the area that is yellowish, it's called the Gini coefficient, which is the area between the Lorenz curve and also the dash red line, as you can see. But how we can apply this Lorenz curve and Gini coefficient to the study of the forest is that whenever the Gini coefficient is close to 0, it's remind us a very even ecosystem. And as far as the Gini coefficient is close to 1, it means that complete and equal ecosystem. There are some papers that talk about how we can apply this Gini coefficient into the study of forests. They actually developed some formula that shows based on which variable that we are collecting from the forest, even it is one-dimensional, two-dimensional, or three-dimensional. One-dimensional like canopy height. They actually develop a formula that shows the maximum entropy or maximum amount of disorder of the Gini coefficient based on the one-dimensional variable of the forest is 0.33. If it is two-dimensional like basal area, it would be 0.5. And for three-dimensional like biomass, it would be 0.6. Based on all of this information, I developed a new formula which called Lorenz-entropy, and it's equal to 1 minus the Gini coefficient that we capture from the full waveform Lorenz-entropy minus the maximum amount of this Gini coefficient based on previous studies. The Lorenz-entropy would have the value between 0 and 1. In this slide, I'm showing you how a fully waveform LiDAR data actually capture the data from the forest. So basically, my study was focusing on land, vegetation, and ice sensor, which called LWIS from NASA. LWIS has 20-meter footprint resolution. So basically, for each 20-meter footprint, the laser actually comes to the ground, capture each data from the forest that is contract, and then bounce back to the sensors. The data collect and create a fully waveform data for us, as you can see in the left side. This study actually hypothesized that based on this ecological succession from early to climax, we can have two different scenarios, from left to the right and from right to the left. If you can see in the graph on the bottom, we have Gini coefficient versus Lorenz entropy. We hypothesize that whenever the Gini coefficient is equal to 0, it means that our forest is complete equal forest. It means that these forests start from the the zero forest start from the shrublands. It means that very equal forest ecosystem then goes to the earliest stage, then intermediate, late, until it captured the climax stage. Another scenario is when we have the Gini coefficient equal to 1 when the forests start to growing. It means that the starting of the forest was from one single nuclear tree, and then from this one single nuclear tree, we have other stages like early, intermediate, late, until the climax stage. We hypothesize that using this actually full waveform LiDAR data and then capture the Lorenz entropy, we can talk about how the entropy of the ecosystem, especially tropical forest, can change from very early stage to the climax stage. Our hypothesis is that as we going through the climax stage, it means that the complexity of the system increasing, and we hypothesize that the value of this Lorenz entropy capture value of 1, no matter from which side we are start, even from the shrublands or nuclear tree, is increasing the entropy until the climax stage capture the value of 1. To prove this hypothesis, we were using some different study areas. One of them was a tropical dry forest, Santa Rosa National Park in Costa Rica, which has 3 different successional stages: early, intermediate, late. And then we had some other study areas like La Selva and Barra Colorado, which was the moist forest, tropical moist forest. And then using the full waveform LiDAR from the LWIS data, we capture different waveform based on these stages from early to climax. When at the first stage you capture the data from the airborne LiDAR, you have elevation versus amplitude, okay? By doing some pre-processing, we capture the relative height of each of the waveform, and then we normalize the cumulative return of this energy from amplitude. In the next step, which is the third column of this graph, as you can see, we create a Lorenz curve based on the normalized cumulative of the height and the normalized cumulative of this return of the energy. From this last column, then we capture the Gini coefficient, which was the area between the dashed line and the Lorenz curve. Putting all of this information together, we capture the Gini coefficient and Lorenz entropy for this study site. And as you can see, we can confirm our hypothesis that whenever we are going from the very first stage, early stage of this tropical forest to the climax stage, we can see relative decreasing in the value of the Gini coefficient to capture the value of 0.33, which showing as a dashed red line here. And then on the other side, your right-hand side, we can see Lorenz entropy versus successional stages, which showing that how the entropy of these different successional stages in increasing, especially when we capture the climax stage, it captured the plateau of 1, which is maximum amount of entropy. And then we can confirm our hypothesis. Plus of using one-dimensional, which was canopy height, using LiDAR, we also analyze a two-dimensional basal area, which is in the left-hand side, and then biomass three-dimensional, which is in right-hand side. And we show that, okay, it is possible to capture the value of the Gini coefficient for each two-dimensional and three-dimensional as well. And we show how the Lorenz curve is changing whenever we go from very early stage to the climax stage, and how we can capture the maximum amount of entropy based on two-dimensional and also the three-dimensional values. Plus of that, in this slide is showing the heat map that how the distribution of the Gini coefficient and Lorenz entropy in these different successional stages is working. And if you pay attention, we can see wherever we have the higher amount of the Gini coefficient, it means that very actually purple side of the Gini coefficient, vice versa, the Lorenz entropy is decreasing. And also, whenever the Gini coefficient is in its maximum, the Lorenz entropy is in its minimum. It means that a Gini coefficient as an index that shows the evenness, Lorenz entropy an index that shows the higher amount of complexity. So whenever we have a very even system, it means that the entropy of that system is higher. Why? Because the complexity of this system is higher, like when we are in the climax stage. And then as a conclusion, the Lorenz entropy can provide a practical tool for ecological monitoring by quantifying entropy using waveform LiDAR data. And also we can say that this index is a useful index to talk about the forest vertical structural complexity. And also we improve that this index can work with forest dynamics as a function of successional stages, plus integrating this index with biomass and basal area can talk about the horizontal structural complexity and productivity of the forest ecosystem. And these two are the reference. One of them, the first one is my paper that published related to that index, and the second one talk about how we can capture the maximum entropy of the Gini coefficient. And yes, that's all for today. Thank you so much for listening to me.
That's awesome. Nice. If folks have any questions, please feel free to drop that in the chat. Thanks, Nooshin. That was a very interesting talk. I was just wondering, would you like to chat more about the differences in the site? I think you had that in one of your slides in front where you spoke about the study sites. Yeah, so what's the key differences in terms of the levels of succession, and how were you able to then correlate your results, and also thinking about transferability to other types of tropical forests? Is that something that you thought of?
Yeah, very good question. Thank you so much. So basically, whenever it comes to defining the different level of forest, it's a very hard work, but so many different variable of the forest should contribute whenever want to actually classify the forest based on the different successional stages, like canopy height, the ages of each trees, basal area of the amount of biomass that each stages create for us. But basically, when we are in the very first stage, early stage, it means that the trees are not in the mature level. So the amount of biomass is less. The canopy height are, especially in our site, was less than 10 meter. And then when it comes to the intermediate, and as you know, the tropical forests are very dense forests. So in intermediate level, we have a very dense forest, and so on until we capture the climax. The climax stage is the stage that you are telling people this forest ecosystem is in maximum amount of complexity. It means that no change cannot happen in this forest stage unless otherwise you are the one that make changes. Like what? Like logging, like logging the trees, or maybe some disaster happened to that forest, and then it's goes off from the climax stage to other stages. Okay, but climax stage, it means that all of the basically species of the trees are in its maximum level of maturity. Nothing can change this forest. And then this Gini coefficient and Lorenz entropy, which comes from this Gini coefficient, talk about these characteristic of the forest. There are lack of the studies about the entropy, and then people was wondering how they can apply this second law of thermodynamics to the study of ecology and biology. And then it's using this Gini coefficient can help us to talk about these variables through the study of the forest ecology. Basically, we are talking that whenever we have a higher amount of complexity, it means that that in the climax stage, for example, all of our forests are in a maximum level of maturity. So we can say that we have a very normal distribution of our forest ecosystem. Otherwise, in the other side, it means that this forest ecosystem has higher amount of entropy, okay, higher amount of heat that happens to these stages, higher amount of disorder.
Awesome, awesome. Thank you. Thank you for that wonderful reply. Kristen, it's all yours now.
All right, great.
Stop sharing.
Yes, please. Thank you so much.
No worries.
Thank you so much, Nooshin. And I don't see that we have any questions in the chat. So let's introduce our next speaker. She'll just get her slides ready here. Okay, so our next speaker is Amanda Belanger, and she is a marine mammal biologist who is passionate about ecological and cetacean research. She obtained her bachelor's in biology and psychology at Dalhousie University, where she studied Amazonian river dolphins for her honors project. She obtained her Master of Science at the University of Manitoba, where her thesis focused on beluga whales. Her first chapter studied the distribution and abundance of Cumberland Sound beluga whales using satellite imagery. In her second chapter, she focused on lipid dynamics of Hudson Bay beluga whale blubber to identify their primary feeding season. She's an avid traveler and has observed whales in the Arctic and Antarctic. Post-graduation, she is now working for Fisheries and Oceans Canada as part of the marine mammal team. She is studying entanglement and collision risk of the endangered North Atlantic right whale and other large whales in the Gulf of St. Lawrence. All right, so go ahead, Amanda, if you're ready.
Sorry, I had too many things up and I couldn't find the Zoom again. Okay. Okay, so I'm going to be presenting on the first chapter of my thesis, which is essentially studying Cumberland Sound beluga whales from space or with satellite imagery. I'm also going to present a few additional components that tied in with this project that were addition to my thesis. So beluga whales are a medium-sized marine mammal that live throughout the Arctic. They have a circumpolar distribution, and there are 7 populations within Canadian waters, and you can see that relative distribution of the Canadian populations in that map there. So during commercial whaling, beluga whales were heavily hunted, so quite a number of these populations have been heavily depleted and remain at small numbers, unfortunately. And beluga whales are also a resource for Inuit in the north, so they hunt the beluga whales and it provides them food and sustenance. So Cumberland Sound is a body of water off of Baffin Island in the Arctic, shown there in the red rectangle. And Cumberland Sound belugas are one of the smallest populations, so they really need to be continually monitored to ensure their continued survival and well-being. And this population spends their summers within the northern fjords of Cumberland Sound, which is the general area is shown in that sort of blue, dark blue box. So 2 of the fjords in particular are Clearwater and Kangle Fjord. So the whales are known to spend their time within Clearwater Fjord up in the northern part, and we hypothesize that there's a reliance on the estuary that's within there, which is sort of that murky white colored river water that you can see flowing into Clearwater Fjord. So estuaries, there's various definitions depending where you look, but they're essentially transition zones where fresh water is mixing with salt water, and these waters are typically warmer than the surrounding salt water. And belugas use various estuaries throughout the Arctic for various potential reasons. So the first one being molting. Belugas go through an annual molt where they're essentially getting rid of that dead, hardened skin on the outside to have that fresh white color underneath. And it's believed that the estuaries help with this, with the warmer waters, as well as the bottom where they're able to scrape along and roll. The estuaries are believed to also be either nursing or calving grounds, as there's a lot of calves in these areas, and the warmer waters may also provide calf thermoregulation benefits. The estuaries also tend to be fairly shallow, so it could help in predator avoidance as well, such as killer whales who may not be able to enter these shallower waters. And the estuaries can also be used for feeding. So my overall objective was to determine the critical habitats of these beluga whales in those northern summer fjords that I pointed out before. So a critical habitat is typically defined as an area that's regularly used by a species of interest, and that's essential to their continued survival and well-being. So we identified these critical habitat areas as those that were consistently part of the core distribution of Cumberland Sound beluga whales each summer, which I'll go into a little bit of detail afterwards. And the second component was to provide an updated abundance estimate. So we really want to monitor this population because I mentioned before, it's endangered and very small. And it's important to identify these critical habitats to ensure where we have minimal disturbance in these areas. So to answer these questions, we use satellite imagery, which is a non-invasive, non-disruptive method of monitoring the whales. And a benefit is that you can only need a few images to cover a really, really large area. And currently, the commercially available resolution is 30 centimeters. So each pixel represents 30 centimeters by 30 centimeters, and this provides us a snapshot in time. It can be difficult to obtain images of the desired area, particularly due to cloud cover, but that's not unsimilar to issues you would get with aerial surveys where you're doing surveys in planes where you can't really fly in poor weather anyways. And satellite imagery is quite expensive. So previously, it was only used for large whale species. So in this paper from Hannah Cubane's, there's a few examples of, in the top left, there are a couple of gray whales. In the top right, we have a fin whale. in the bottom left, we have a couple of humpbacks here, and then there's a southern right whale in the bottom right corner. So my advisor, Courtney Watt, she decided to try this out with beluga whales, and it had been a success. So she wanted to continue that with various projects, one of those being part of my thesis. So we had images from 2020 for just Clearwater Fjord, and then 2021 and 2022 for Clearwater Fjord, Kangerluarsuk Fjord, and a little bit of the surrounding waters, with most of the images being 30 centimeters, but 2022 being slightly lower in resolution. So within our images, we had to go and identify all the beluga whales. So this is what they would typically look like. It's a bit poorer quality in this presentation than it would be in the actual images, just from cropping and such, but this is fairly what they would look like. So you have 5 individuals in this picture, and then a sort of a group on the right-hand side. So identifying belugas can sometimes be a bit difficult. So this looks like it could be a group of beluga whales together, especially on the right side. It looks like a long individual that could be a whale. But using contextual clues, if we zoom out in this case, we can see that this is actually just waves off of the side of a large influx of water. So those are definitely not beluga whales. Another example where you can use clues, contextual clues, to identify whether something is a whale. So here I've pointed out 2 objects that are white and long and have a general beluga shape. But if we look a few days later, as September 7th, those objects are in the exact same location, and 2 additional ones as well. So we know that these are definitely rocks and not whales. And if we zoom out, you can see that it's quite shallow in this area. And so the whales likely wouldn't be able to even get up to that spot. Another example of things to look for identifying belugas is essentially pod formations. So groups of whales together helps identify other whales that are nearby. So once we've identified all our beluga whale locations, I ran kernel density estimates. So these are essentially maps of a utilization distribution. So based on the observed points, it gives us how likely it is for an animal to use a certain area. I then wanted our core range, which is our 50% in the dark purple, and then home range, which is the 95% in the light purple. So essentially I was finding the minimum density for 50% of the points from the kernel density estimate, and that gives us our home range, and then the minimum density for 95% of the points, which gives us the home range. So core range is 50%, home range is 95%. And this kind of gets rid of any outliers instead of using 100%. So if we take a look at Clearwater Fjord in 2020, the distribution is fairly similar between the 2 dates, with a slightly tighter aggregation on August 30th. 2021, the whales seem to be more tightly aggregated, as well as being more central to Clearwater Fjord than the previous year. 2022, again, similar distribution in that central portion. So when we look at all the dates, the 5 dates that we had side by side, we can see that in almost all of these dates, the whales were really present, especially in that 50% core distribution in the central part of the fjord, and in 2020, also in a secondary bay to the east. So when we overlay the river plume or the estuary plume, we can see that it changes from day to day, the shape and size and extent. But we can see that the dark purple, so our core distribution, is almost always within the estuary or next to it. So they're really staying around that freshwater plume. So we also had aerial survey data from previous studies. So I wanted to look briefly at where the whales were observed in those as well. So in 1999, again, on August 6th, we had the whales in that most eastern bay on August 7th as well, but the distribution moved a little bit more over towards the central part. And then on August 8th, most of the whales were really in that central part of Clearwater Fjord. 2024, very similar. A lot of whales in that central portion. The map is just a little bit tilted here, just to orient yourselves. And again, a lot of those whales in that secondary bay as well. And same thing in 2017. So really the majority of those whales are staying within the central part where the estuary is, or just to the side in that secondary bay. So it's quite evident that they're using the estuary and the main plume, but it wasn't quite clear why they were also moving to Shimlick Bay. That eastern bay, it's about 4 to 6 kilometers away. So it's definitely traversable within a day. And so I looked at things like time of day or tide cycles, but those didn't really seem to have an impact on when the belugas were in each of the different locations. Other possible reasons could be movement of prey between the two. There might be salinity exposure, so they might be moving away from the estuary plume if there's too much freshwater exposure for whatever reason, or temperature exposure. So I mentioned before that estuaries are typically warm waters, but the interesting thing about this estuary is that the river inflow is directly from the glacier. So it's understood these waters are actually really, really cold and probably colder than the surrounding salt water. So they may be moving to the secondary bay for slightly warmer waters. When we take a zoom out and look at the extent of the rest of the fjords in that northern portion, we can see that that Clearwater Fjord at the top part over here is really consistently part of that core distribution, even at a larger scale, and that freshwater plume area. Within Kangaloo Fjord and the other surrounding waters, there weren't really any areas that were consistently used by the belugas. The groups that were identified were really quite small and quite spread out, and nothing was very consistent. So it's really only Clearwater Fjord in that central part that was consistent to their distribution again and again. So the next part was an abundance estimate. So when calculating an abundance estimate for whales, you can't simply count the individuals that you see at the surface, because the whales tend to spend most of their time underwater where you can't see them. So you have to account for those within your abundance estimates by applying a availability bias correction factor. So based on dive data, we know how long the whales are spending at various depths and how long they're spending at the surface. And this allows us to know how large our correction factor should be when applying it to our abundance estimates. So with aerial surveys in planes, we can typically see the whales up to 5 meters deep. So it's not just how much time they're spending at the surface, but how much time they're spending in the top 5 meters of the water. But with satellite imagery, we didn't know how deep we could actually see the whales, so we didn't know which kind of correction factor we would need to apply. So another student, Jordan Stewart, that was part of his thesis, is determining how deep we could actually see these whales within the satellite imagery. So they had beluga cutouts made out of sort of fabric and wood, and they placed them in a lake. So they had 3 of them in a clear lake, one at 1 meter, 2 meter, and 4 meter, and then in a turbid lake at 1 meter and 2 meter. So in the top sort of 4 pictures, you can see in the yellow and blue circles are the whales at 1 and 2 meters deep, and those are very clearly identifiable. But the one at 4 meters deep was not. So you can kind of see it a little bit with sort of a white dot, but you wouldn't be able to confidently say that that is a beluga in these images. And then within the turbid lake, it's very similar. You can kind of see some darker white spots, but you wouldn't be able to confidently see, confidently identify that this is a whale. So the whales were determined to be detectable in 1 and 2 meters deep in clear water and not identifiable in turbid water. So how does this apply to Cumberland Sound and abundance estimates? So in all of Cumberland Sound, we assumed that the whales were visible up to 2 meters deep, except in the estuary. So the actual physical plume, where it's a lot darker and you really only can see the whales at the surface, would have a stronger correction factor because you would see fewer whales in your location. So we had more than just the top fjords imaged in 2021. So everything that has a color on this map was an area that was imaged, and it was essentially extrapolated to the rest of Cumberland Sound to provide an abundance estimate. Our abundance estimate was approximately 1,700 individuals, which was larger than the previous estimate in 2017, which is closer to 1,400. However, they surveyed a much smaller area. So as sort of a direct comparison, the exact area coverage that they did in the aerial survey, our abundance estimate is about 1,200 individuals. So it is a fairly similar estimate to 2017, which is a good sign. So hopefully it means that the population is not declining too much. So overall, the distribution of belugas can definitely vary from day to day and also across years, but the belugas were always observed in Clearwater Fjord. And in the 2 years that we imaged the other fjords, they were also present in these areas, just not in a consistent location. And so we present the Clearwater Fjord estuary as a critical habitat and that neighboring Shimlick Bay as an important habitat, especially with additional support from those previous aerial surveys. And then all three of those studies are published as the abundance estimate, the distribution, and then Jordan's satellite imagery work with drones and other stuff has been published as well. Thank you.
Great presentation. Thank you, Amanda. And I see that Alex has put some questions in the chat. I can read those out, or if Alex would like to go on mic and ask as well.
Yeah, you can read it out, Christine. That's fine.
Okay, so excellent presentation, Amanda. How do you identify the whales from satellite images? Was this based solely on visual inspection or some form of image analysis? Have you thought about using deep learning techniques for this mapping? Also, did you explore the use of multi-temporal images for the visualization? And do you have plans to incorporate traditional knowledge from the indigenous communities in the region? This would provide valuable insight into whale migratory patterns.
Yeah, so for the first part on identifying the whales, so essentially we have the image it was ArcGIS or ArcMap at the time, but that doesn't exist anymore. But yeah, so essentially we had a grid overlaid and we went through the grid and we identified all the items of interest, and we would mark what we thought was a confident whale, what we were confident as being a whale, and some things that we were less confident. And then a second person would go through and read all those points and say whether they agreed or disagreed. They're working on automation of this with sort of what's the word? With AI, I guess, essentially. But it's very, very tricky, especially when there's a lot of waves. It is also tricky to do that with just your eyes, but I think it's still a work in progress on that side. Multi-temporal images for visualization. What do you mean by multi-temporal?
More like multi-date images, so not just using a static capture, right, of the area, but having like the same image captured at different times of the year. So you could have that based on your knowledge of the whales and how they move around in the your study area. So was it just a one period snapshot, or did you have multiple snapshots in a year?
So what I showed are essentially the images that we had. It's quite difficult to get the images. So I think we had tasked multiple for 2022, and we only ended up getting the one, and it was only at 50 centimeters. When we always ask for 30 centimeters, the best. So essentially Maxar is the company that owns the satellites, and they prioritize different things and based on various things. So I don't really know how, but yeah, so it is quite difficult to get those images, unfortunately. So that's why I just kind of compared what I had and see if there's any,
which is fair. I was just interested. I really wanted to know if that was done, because that would add some value. I know there's a cost implication and also data availability issues. Those are some things to also consider, but you could also look at other vendors. I'm not here to market vendors, but you could look at PlanetScope. That's another option, and see what they have. Just something to think about, though.
Yeah. Okay.
Yeah.
Good to know. And then the last question. So I mean, the fact that the whales are actually in Clearwater Fjord at the northern part of Cumberland Sound is kind of fairly well-known knowledge, and basically mainly comes from the indigenous people that are there, as well as for the abundance estimate. Just want to get this right. So essentially, here, I'll go back to the slide. So there's different kind of quadrants, if you can see in sort of the light gray lines. And so each one kind of had, so we had to extrapolate, obviously, because we didn't cover the whole area in images. And basically the weight of each area that went into the final abundance estimate was based on indigenous knowledge and where they say the whales are actually spending their time. So if they're really not spending a lot of time in one of these quadrants, then it had a lower weight in the overall abundance estimate. Yeah, awesome. And then so Courtney works very closely with this community and all the work that's done up there, and there's quite a few other projects that
nice.
occur up there.
Yeah, that's awesome. If you'll be able to share some of those studies that have been done, I think the audience will be interested. I would be interested in knowing about that myself. But yeah, it's always very nice to see how well you're able to complement traditional knowledge and also Western science. There's a very good harmony between both of them, right? And that informs your study even better. But yeah, wonderful presentation, Amanda. You guys are doing some awesome work. Nice.
Great, thank you. Are there any other questions from our audience? Don't think so. I'd like to thank our speakers, both Amanda and Nooshin. Thank you for sharing with us your studies, and it's really great to see that and something different from what some of us do from day to day in GIS, right? So I will thank you and thank everybody who attended here today. And we would like to promote, URISA Alberta would like to promote our next webinar of the series for 2025, and that will be on April 29th, 2025, and we will have Dr. Joseph Kursky, and he will be presenting on the 5 forces, 5 trends, and 5 skills in GIS. So check our LinkedIn page for updates on that and a Zoom link to register, and we hope to see you there. Alex, do you have any final remarks?
Oh, no, just to say thank you to everyone for attending. Thanks to the speakers. You guys are doing some awesome work. I'm happy to see publications coming out of your research. That's very nice products to have. And yeah, looking forward to more things as you advance in your fields of study. Thank you. And thanks to everyone for attending.